Okay, welcome everyone. This is CSCE 611. My name is Jason Bakos. I'm the instructor. I also have two teaching assistants, Charles Daniels, who's right here, and Philip Conrad, who is not here.
He said he was coming,
but he might be running late. If he walks in, I'll point him out. The teaching assistants will be helping you out in the labs, and I will be delivering the lectures. Okay, so my plan for today is to read over the syllabus, and then I will briefly introduce the class, and then I'm going to start in on our first topic, which is a review of some 212 material. So, whoops, hold on one second, grab the syllabus.
Thank you.
There you go. Okay, section 1 is the catalog description. This is a hardware design course, so we'll be learning about design for logic systems, emphasis on high-level CAD tools, such as hardware description language, so you'll be learning another programming language called System Verilog in this course. And we'll be using tools to deploy hardware designs to a field programmable gate array. And functional modeling. So we'll be learning this new language and then synthesizing it, deploying it on hardware, and of course also testing it in simulation. Some of you registered for section 1, some of you registered for section 2. If you're in section 1, your lab time is Wednesdays at 3:55 to 5:10 in SWIR Engine 3D22, and if you're in section 2, your lab time is Thursdays, 3:55 to 5:10, and of course everyone will meet for lectures on Mondays at this time. I believe the lab combination is still the same as it was last semester, so 51243 in case the doors are closed. I think they're usually closed, even if there's people in there, so that'll get you in. I'm sorry? It's on the syllabus under section 2. It's 51243. You hit each of those numbers individually in sequence to open the door. Okay, so we're going to be using Moodle, the dropbox.csc.sc.edu. The name of that software is Moodle. I think you're probably all familiar with that. That's the departmental teaching site. I've got it up right here. This is what it looks like when you log in. I believe everyone logs into the same Moodle page. I confirm that because everyone's enrolled. So regardless of what section you're in, you'll come into the same page. So meaning that if you post anything in like the discussion forums, the class as a whole will see it. I'll post all the downloads, lectures, assignments, grades, submissions are all through Moodle. I don't use Blackboard for anything. Yes?
The code changed.
Sorry?
The code changed for Lord.
Oh, it did? Okay.
45213.
45123?
213.
45213. 45213. Okay, that's the first time they've changed it in a long time. Thank you. So basically, I'll keep this page updated all semester, you should be logging into that fairly regularly. We also will have discussion forums, and you can ask questions on there. I post the lecture slides. Oh, and I also have a link here to the only other website that you may need to go to is I have a YouTube channel, and I've posted every lecture from the last 3 years of this class. So if you're interested in kind of reading ahead to see what's coming, you're welcome to go and check that out. I'll also be posting all of the lectures I give this semester on there as well. Just in case you miss class, or if you want to hear what I said again, you can log into the YouTube channel and you can check it out again. I share this, I have the slides and the audio on there. Okay, the textbook is Digital Design and Computer Architecture. I'm not assigning any problems out of the book this semester, so it's technically required, but if you don't have it, it's not, it wouldn't be catastrophic. It does serve as a good reference, though, for System Verilog, which is the language that we're using in the class. Yes?
I have some experience with VHDL. Can I use that language for Verilog?
Sure, you can use VHDL. Yeah, I have no problem with that. They're equivalent. I used to teach this course in VHDL. I switched to Verilog because it seemed that Verilog was kind of becoming more popular in industry.
The comment I would have don't care. But if you say, oh, why does this have a syntax error? I'm just going to have to shrug my shoulders. So.
Okay, section 5, course learning outcomes. This is kind of just a more specific, it's a more specific version of the catalog description. We're learning HDL, as I mentioned. We used to use Verilog. Now we went from VHDL to Verilog to System Verilog. So over the years, I have evolved the content. We've refined things. We're going to be talking about simulation and verification, microarchitecture. So the objective of this course is essentially to design a CPU from scratch and deploy it on a chip and run it. That's the idea. So that involves design, simulation, synthesis. I've got a bunch of dates here. These are all the significant dates. They're in chronological order. Obviously, lab was canceled last Thursday when the semester started. Likewise, when we have fall break, which is Thursday and Friday, I went ahead and just canceled the Wednesday lab, so that way, if you're in the Wednesday lab, you're not getting an extra session as compared to the Thursday crowd. So we've got those two cancellations. Of course, we've got Labor Day coming up on September 6th. Lab will be canceled this week as we kind of spin up the course, but we will have lab next week. And then I think the only cancellation we have here, is that Philip? Yeah, oh, there's Philip. Philip is the other TA. Philip, that's Philip Conrad. The only cancellation we have that's not a university closure is on November 15th, where I will be away at a conference. And there's a chance that the TAs will also be gone, but we don't know that, right? You guys are still trying to work out the travel?
I got the whole assignment thing, so I'll be gone 2 weeks.
Okay, and Philip?
Still waiting on travel funding.
Okay, so we may have some lab closures around that time as well. But for sure, we'll have no lecture on November 15th because I'll be running a workshop at Supercomputing. And the last day to turn in projects is December 3rd. That's an important one to know. And the final exam is on December 6th, which is the first day of finals week. So you get this final done early. Yes?
Any separate dates for each lab, or you have like final project cut-off date for all the labs?
For all the labs. So I'm gonna talk more about that in a minute. But basically, you can turn in labs anytime you want, but you have to have them turned in by December 3rd. Ideally, you turn them in when they're due, but the problem is they build on top of one another, so if you get behind on one, it has a domino effect on future labs, so it's not uncommon for students to turn in labs late. But I'll talk more about that late policy here in a moment. Okay, I've got section 7 is contact information for me and for the two TAs. They are going to have, the office hours are listed here by appointment currently, but Charles just mentioned that there will be regular office hours scheduled in which the TAs will physically be in the lab for you to come and ask questions. Do you know where those are yet, or are we still?
I think we're going to plan to hold them in 3D22. It'll probably be like Monday, Tuesday afternoon. We will have a time by next week when labs start up. And you guys can just kind of show up whenever you want. It'll be in the same room the labs. And that way, 4 out of the 5 days of the week, you'll have a time that you can come and get help with the lab if you need it.
Yeah, and
plus appointments, obviously, if you need that.
Yeah, you can make appointments. Their email addresses are here. All of our offices are in the Story building up a block. So one of the reasons for that is because when we're in the lab sessions, sometimes you'll have a question that won't get answered by the end of the lab session, just because sometimes it takes a while to solve problems, and so that the office hours will be useful for that. Hopefully that doesn't happen often, but it does happen. Okay, so most of your grade for this course will be comprised of 5 projects. You will be working on those projects in teams, in groups of 2. So both partners in each group will share the grades for these labs. If you're taking this course for graduate credit, then there will be a 6th lab, which is mandated by the university. You have to do, an additional project in order to get graduate credit, and we do have one specifically for that. But probably all of you will just have the 5 labs. Then we have quizzes, which will be given on Moodle. I generally leave them open for a week just to review content from the lectures. There's a midterm and a final exam. Quizzes, midterm, final exam will be individual grades, and as I mentioned, the labs will be a shared grade between you and your partner. Yes?
How many quizzes we will have?
I try to do one a week, so hopefully we'll have around 10. I think in practice, though, it's usually like 7.
Not quiz for this week, right?
Sorry?
Not quiz for this week. It's starting from
No, not this week. That's right. Next week, though, I'll have one. Now, you'll notice that these numbers, if you add up all these weights, they add up to 115%. And the reason for that is because if you get behind, or if you have a partner that's not contributing, you can opt out of the last lab, right? You can basically just not turn it in, and you won't be penalized. You'll still have a maximum potential score of 100%. Likewise, if you do really poorly on the midterm or final, basically it doesn't count, right? It's essentially dropped. Also, if you're satisfied with your score by the end of the semester, you don't have to take the final exam. So these weights all add up to 115%, and then the grading scale I use will be the standard grading scale. Yes? Yes, question.
Can undergraduates team up with graduates or no? How many graduates in this class?
I haven't checked yet. How many? Raise your hand if you're taking it for grad credit. Oh, more than I expected. 1, 2, 3, 4, 5, 6. Okay, well, we have an even number. So hopefully we can do we can have 3 teams of grad students. I don't know if you guys are all in the same lab, though. Odds are you aren't.
Team up with another graduate student?
No, with other grad students.
So no undergrad? No.
Well, if we have to, I mean, sometimes it's unavoidable, but if that happens, then only the graduate student part of the team is responsible for the last lab. Now, luckily, the last lab is designed to be fairly easy to do if you've finished Lab 5. Basically, the idea is that you design a CPU, and then in Lab 6, you scale it up to a superscalar CPU, where you basically copy and paste the hardware, and you have it execute 2 instructions per cycle. It's not real difficult, so it could be handled by just one team member if you've got a graduate and undergraduate student in the same team. Does that answer your question?
Yes.
Okay, good. Okay, so we've got. Oh yeah, and obviously because the grad students have an additional lab, the weights are different, but they still add up to 115%, right? So this way you can basically customize the course to have more of an emphasis on the individual scores or the team scores, or the design work versus the conceptual work, right? So it allows some for customization. Yes?
So are you going to test this for the midterm on the Moodle, or is it in class?
Oh, the midterm is actually a traditional midterm. That's how we've done it in the past, right? Yeah, that's how we usually do it. Yeah. Yeah. Although, yeah, I mean that's actually, you know what? Well, last semester when we were remote learning, we did the midterm online. I was planning on doing it in person, although it is kind of. I mean, now that I'm here, it's pretty cramped in here. I don't know. Might be more realistic to do it online. So now that you mention that, we probably go out to do the midterm online. The difference between the midterm and the quizzes, though, is that the quizzes, I give you a week to do them, and they're short. The midterm is, once you start it, you have 75 minutes to finish it. So you have that time constraint, but it's still done online. The problem with doing it online is we do it through midterm, the Moodle rather, and it's multiple choice when I do it online. And so obviously if you're here doing the midterm, I can ask better questions because I can have you sketch out a circuit, or I can have you write some code. And so that's better for you guys. It's a better way to assess your knowledge, but like I said, I think it's a little crowded in here to do in person. You have a question? Oh, sorry, you did.
So there's going to be 2 tries, like 317, or
2 tries, yeah. Yeah, 2 attempts.
2 attempts for what?
2 attempts where you basically can, you submit it, it tells you what your score is, and then you can try a second time. The quizzes, yeah.
Not the midterm.
Not the midterm, right? And midterm is one try.
1 and done.
Yeah, 1 and done, that's right. Okay, so I've got this schedule here. Now, if you If you compare this against what I've got on YouTube, it's a little different, but the topics are still the same. I rearranged things a little bit because I noticed that last semester we have some weakness in the assembly language programming area, so I moved that up front this semester. But if you do want to go online and see it presented in a different way, you can still find all this stuff on my YouTube channel. I've got lectures on all this stuff. But basically, we're going to start out with, like I said, reviewing some 212 material on assembly language programming, and also we're going to be learning about a new architecture called RISC-V, which is a little bit different. Yes?
What kind of assembly language you use? Like what?
Assembly language?
Yeah.
We're using RISC-V for the language, and we have a simulator called RARS that you're actually going to write your code in and run it in.
One more question. Should you necessarily attend the lab, or you can just install environment on your computer and do everything in simulation in your computer?
You can do that, yes. Yeah, as a matter of fact, we even have a virtual machine image that I still use when I test this stuff out that you can download. This is a virtual box. Yeah, it's still got the right link on it. Just want to double check. So you double click that and you can download a machine image and run the code. It would be hard to work with a partner if you're doing that, obviously, and you wouldn't have the boards. So the projects are going to be graded by demo. So you're going to do your design, you're going to deploy your design onto these FPGA boards, and then you're going to demo them for the TAs. So at some point you'll have to do that. But like I said, you can use the software at home for doing the design and simulation work.
You can do design at home, then go to the lab, try your design on a real hardware, and if it works, present it to you.
That's right. Yep. Yeah, absolutely.
And do test it before you put a demo in, because the simulator is good, but it's not perfect. So always make sure that it actually runs on real hardware. We've had that happen before. Somebody goes, oh, it works in the simulator, and then you run it, and then it just doesn't work.
Thank you.
Okay, so you'll notice that if you look at the schedule, you'll see that the first 11 weeks or so of this course are mostly just going to be concepts that you need to do the labs. So it's going to be very applied for the first two-thirds of the semester. And in the last third of the semester, the last 5 weeks, it will be almost entirely conceptual while you finish the labs, right? While you finish the projects, right? So we're going to front load this with a lot of applied stuff. Like this is how, you type this in, you run this, you click that, you do that. Very applied. And then we're going to switch into conceptual mode in the end of the semester. So there will be a tonal shift here around November 1st or so. You'll notice right after the midterm. All the labs are there. You can see that I've allocated two lab sessions for Lab 1, Lab 2, and Lab 3, and I've got 3 lab sessions for Labs 4 and 5. So keep that in mind because it generally takes longer than 2 lab sessions or 3 lab sessions to do one of these labs. So you're probably going to have to visit the lab outside of the scheduled time, or as she said, work from home if you can set up an environment on your home machine. So I just want to make sure that that our expectations are realistic. Okay, so if you have any disabilities that require extra time for exams or anything else, contact the office. I've got the phone number for that. There's obviously, as you guys I'm sure all are imagining, there's a chance that things will change radically before the semester ends and we'll be at home again. So obviously, if that happens, we'll make adjustments. We have taught this course remotely once last fall, and not real thrilled with how it turned out, but we got it done. So we can make that adjustment if necessary.
How do you do labs virtually?
We have a virtual, so Charles has developed a virtual version of this board that you can run entirely in simulation. The feedback we got on it wasn't great, but also it was we had to do it like pretty quickly. It was kind of a beta. Hopefully we'll have time to refine that a little bit more if we have to rely on that exclusively. But that's essentially how we did it. We created a virtual, but we had to do it ourselves. There wasn't anything off the shelf to do that with, unfortunately. There was no, surprisingly, there was no virtual version. No one had ever done that before, essentially. Is there a question? Yes?
If some students they will drop out of your schedule, can you make up for, let's say, appear at Wednesday, or if your Wednesday drops out, can you appear on Thursday in a the opposite section lab?
Oh, yeah, great question. In the past, it's never been an issue. We're almost at capacity now, though. That's the only issue with doing that is if the room is filled. The lab, I think we have 25 workstations in the lab. Or 20, 25?
I don't remember.
Something like that.
The maximum occupancy on the room is 30, but I don't know.
Oh, okay.
If there are any physical computers in the room.
Is that the fire department limit, or is that the COVID limit? Okay, yeah, so there's a capacity of 30. So we're going to be close to capacity, assuming everyone shows up to lab. So that's the only problem with switching, right? I mean, I have no problem with it, but like we can't throw someone out that's actually supposed to be there for someone that's switching sections. Yeah.
Also, I think Philip and I should be in both lab sessions most of the time, unless one of us is ill for some reason. So if there's one of us that you find easier to follow or something, it should be the same.
Yeah, they're going to be everyone in the lab is going to be doing the same thing in both sections. So ostensibly you can go to wherever you want as long as it's not filled. Okay, I mentioned electronic resources. We're using Dropbox.csce.sc.edu, not Blackboard. Not a big fan of Blackboard. I did use Blackboard last semester for a whole course, but I prefer Moodle. There's an announcements forum on Moodle that forces everyone to subscribe, meaning that if I post something in there, it emails you. So hopefully you guys you can receive those emails. Make sure that you check your university email or forward it or whatever, for announcements in case we have a postponement of a due date or whatever I have to get out there. Gradings, where I use the standard grading scale, 90, 85, 90, 85, 80, 85, 75. Obviously, the upper limit is 115, but there's no, there's no advantage to trying to, hit 115%. Except for if I write you a recommendation letter, I typically will put in there, this student took my class and they were the 6th highest score in the class out of 58 or something like that. So that would be the only advantage of trying to push it higher. But yeah, I mean, basically anything over 90 is an A. So this class has kind of a unique academic honesty policy. And it's because we're using CAD tools. And CAD tools are designed by engineers, and engineers can't program for shit, basically. And so it doesn't matter how many decades have gone by, the CAD tools are terrible. Always have been, and I guess they always will be. So you're going to run into trouble with the CAD tools, and this is why I mentioned earlier that sometimes you'll have a question for the TA, and the TA will be trying to answer your question for half an hour because there's obscure, weird corner cases, weird things that come up with the CAD tools. Sometimes your design won't compile, and you'll get an error message that is just not very descriptive, right? So I don't mind if you help out other students with overcoming these problems with the tools, right? And in fact, that's one of the nice things about working in lab, and I think that's why everyone was so miserable last fall working at home in isolation, is because there's no one to ask questions, from, right? With these tools and the weird things that happen, and it's tough. So when you're in the lab, you can ask your next door neighbor, hey, have you seen this error? Or you have a way around this. That's fine, but obviously you can't copy code. You can't plagiarize, and we run Moss, or Charles has a script he runs. Yeah, so make sure you don't copy anyone's code. But I have no problem with you guys, helping each other out, overcome technical issues with the tools. And obviously, both partners in the group are submitting the same design, the same project. In fact, only one of you actually have to submit. So each team only makes one submission. So when we get the submissions in, we may have 50 students. We only grade 25 submissions because the groups only submit one project. Yes?
As further discouragement to cheating, there's almost always at least 3 different ways to do literally anything in Verilog. So if you try to copy from another group, you may not understand how they were doing what they were doing, or you may only get part of a larger thing that you actually need in order for it to work correctly. And yeah, like it's not a good look if we see segments of code that are in a completely different style from the rest and don't look like techniques that you've been using before. However you're solving it, keep going through and finish it that way. Just be consistent, and that honestly goes a long way towards helping debug stuff. Because if you're wrong, you'll be consistently wrong, and then when you figure out what's wrong, you can fix it everywhere.
All right, thank you. Question?
What if two groups copy the same code from the same Stack Overflow page?
So that's a fun one.
Just put a comment and say where you got it from. Everybody Google stuff. Google stuff. If anybody told you you're not supposed to Google stuff, that person was wrong. Just make sure you cite your sources if you're doing something. And obviously, if you copy paste the lab description and like find somebody that leaked an old submission on GitHub or something, like we have Google too. Don't. It's fine to Google. Oh, why am I getting this syntax error or something, and like copy over a 3-line fix. It's different if you're pulling over like a whole module of code that's like some kind of non-trivial design you're supposed to come up with on your own. It's usually pretty clear when you're looking at it. Like if you see like a huge block that's been pulled over. So.
It hasn't really come up though. I mean, I don't think there's a lot of system Verilog on Stack Overflow. This is an obscure programming. This is a niche programming language. So you probably won't find that much. I mean, there are resources online that you can go for help, but in terms of actually finding complete working code, it's not quite the same as like when you take Java. Okay, so we've got, in terms of lab attendance, lecture attendance, as I mentioned, I put all the lectures online, assuming I don't have a technical snafu and lose my recording for whatever reason. That hasn't happened yet. So if you're not comfortable in being packed in this room, you're more than welcome to watch the lectures online. So the lectures are optional. Lab time is also optional, but you're going to be working with a partner, and it would be best not to let them down. The lab is pretty big. I don't know. You guys have probably seen 3D22. It's pretty big space. It's pretty sparse in there, so it's not as cramped as it is in here. So you have the option, like I said, assuming that my recording goes through and everything, you could watch the lectures online and then just come to lab. Let's see, I mentioned the group work policy. Try to choose your group partner wisely. Start thinking about that now. We're going to need the partners, we're going to need the groups for next week because we're going to start labs. Both members of the group receive the same grade on the labs. Don't expect both members to contribute exactly equally because it's not even possible, right? I mean, you always have one person that contributes more than the other. Hopefully, it's more like 60-40 and less like 95-5, right? But try to be careful with your lab partner. And project submissions. Okay, this is a little bit unique too for this class. First of all, submitted projects have to compile to receive any partial credit. Obviously, grading this stuff is tricky. It's hard to award partial credit if something doesn't work. So you kind of have to go in the code and try to grade based on rubrics, which we found that to be difficult. But at least it has to compile to receive partial credit. Each student the labs have to be submitted on Dropbox by 11:59 p.m. on the due date. Late projects are charged a 7.5% late penalty for each school day, not including weekends or holidays, after the due date, but it's capped at 30%. And we do this because the labs build on top of one another. So you can't, if you get stuck on a lab, you can't skip it and go to the next one. So if you get behind, on one lab, you're probably going to get behind on the next lab and the next lab. So that's why we cap the late penalty at 30%. Okay, and it's also the reason why we have the maximum weight is 115%. Yes.
The project is the same as the lab 6 or graduate. The lab 6 and a project.
No, labs, yeah, so the naming is confusing. We call them labs, but they're really projects. A lot of times I'll say labs. So lab 6 is the graduate lab/project. Yeah, it's basically, what we're looking for is a design that you turn in.
Each of us has to submit it, but for 1 to 5, one of the two things are missing.
Right, that's correct.
Only for 6, everyone for 6.
That's correct, yeah, yes. Yeah. Okay, so only one student, only one submission per any project. We had cases in the past where students try to game the system a little bit. You know, it's like, well, I could turn it in, you know, I'll turn in one version, then I'll turn another version late, and I might actually get a higher score for the late one. And, you know, just one. We're trying to, you know, we have to keep the workload reasonable for the TA, so only one submission per project. And you have to submit them all by December 3rd, as I mentioned, because we have to have enough time to grade them by the due date for the grades. Okay, that's it. Any questions?
All 6 by December 3rd.
Yes, all submissions have to be in by 11:59 on December 3rd.
But if you have done them piecemeal and submitted them, that's it.
Yes, yeah, yep. Okay, so let's go ahead and jump into some material. Hello? Yes?
So the slides will be posted on a Blackboard, or we should look for them on your webpage?
Oh, the slides are on Moodle, the Dropbox, not on Blackboard. And yes, they are on there. The PDFs of all these are on there. That's weird. Got a blank screen. I've never seen that before. There we go. Okay, so I always like to start this course off with motivating this material. Why are you taking this? Every class I teach, I always start out with explaining why you're taking the class. So as I mentioned, this is a hardware design class. This is what I consider to be the quintessential computer engineering class. If this class isn't interesting to you, or if you really don't like this stuff, then you're in the wrong major, most likely. This is the epitome of computer engineering. We're going to be doing hardware, software, co-design, basically building a CPU from scratch. But you know, it's still a legitimate question to ask. Why are we learning about hardware design? Because in our field, there's this concept of Turing completeness, meaning that you can buy a CPU off the shelf and it can solve any problem that any other computer can solve. Meaning that you can solve any computable problem by and realize a system for doing that just by writing software. You don't have to design hardware, right? So when do we have to design hardware? So in this case, I got an example. You could buy you could take any computer off the shelf. Anything from a supercomputer like the Summit supercomputer all the way down to an 8-bit microcontroller, and they can all run the same code, they can all solve the same problems. The only difference is the performance and the energy efficiency. And you might be surprised to know that the supercomputers, the large-scale computers, are actually much more efficient than the smaller embedded computers because they can take advantage of economies of scale, essentially, right? So there is a difference in performance, right? But CPUs tend to get faster over time, right? So if the computer you've got isn't fast enough, then you just you wait a year and buy a new one. It'll be faster. The problem is, and I probably most of you know this by now. This used to be more of a shocking revelation back years ago. But CPUs are not really getting faster anymore. The rate of improvement is slowing down quite a bit, and this is I really love this chart. Hennessy and Patterson, who wrote the architecture textbook, put this together, and this is plotting the speed up of these computers relative to the AT11-780, which I believe was a VAX machine. So that's one. And then so this, like for example, this machine is 280 times faster than that for whatever benchmark they're running, right? And so they plotted all these things, and this is a little out of date. It goes to 2018, but they also divided it into segments showing the rate of the average rate of improvement over that segment. And obviously you could you could move these segments around if you wanted to, but you could see that from 1986 to 2002. These machines were improving at a rate of 52% per year. And in fact, that's, if you think of Moore's Law, if you've ever heard of Moore's Law, it says the capabilities of a processor double every 2 years. That's actually faster than Moore's Law, because that would be an improvement rate of a square root of 2, which is like 41% per year. 52% per year that's a huge rate if every single generation is improving at a rate of 52%. But then it slows down. You can see it's 23% from 2003 to 2011, and then 12% and 3.5%. So machines are basically not getting any, general purpose CPUs aren't getting faster anymore, or they are, but at a very low rate. And so what this is showing, these are actually benchmark results. These are run times. They actually ran a program and they timed it, and this is the times essentially. But I actually came up with my own chart, which I think is a little bit more, in my opinion, it's a little bit more insightful. So I went back and I looked at the last 10 years of Intel processor architectures. So this is from Westmere to Coffee Lake. Now, and again, it's a little bit out of date. We're on the 11th generation now, and that goes to the 9th generation. But it's basically the 10-year period from 2010 to 2020. And I plotted the technology column, which is the fabrication technology. This is really what Moore's Law is talking about, the number of transistors you can fit on the chip. And I calculated the rate of improvement over that 10-year period, much the same way that Hennessy and Patterson did, except I just based it on the technology, not on the benchmark run times. And you can see that the rate of improvement there was, over that period, is 17%, which means that the technology doubles, the number of transistors is doubling every 4 years at that rate, right? Which is close. I mean, it's not the 2 years, but it's still, Moore's Law is continuing to move forward. It hasn't stopped yet. Yes?
Where are you getting the 4 years from here?
I took the difference and I took the, basically the 10th root, essentially, all right? And also you have to consider the fact that this, this nanometer number here is the length of the transistor. There's also a width, because they're two-dimensional devices, it scales down at the same rate. So if you're looking at area, it's actually scaling down at the, basically the inverse, inverse square of this number, right? So based on that, if you're looking at how the area is scaling down over this period, on average, it's improving by 17% per year, which gives you a doubling rate of every 4 years. But the problem, though, is that some of you guys might be following the news. You know that Intel is having some issues moving this down. Smaller than 14 nanometers. It's last couple of years they've had some problems in their fabrication. So maybe I don't know, maybe things will stall out big time with Moore's Law. But over this 10-year period, my premise is that's still going. But if you look at all the other performance indicators, which basically predict not the actual performance like Hennessy and Patterson use, like that plot, these are actual run times here. But what I'm looking at here these are the performance indicators that indicate the maximum potential performance, the upper bound, right, that you can possibly get. It's not the same as the actual performance, but this is the potential. And so for example, you look at clock rate, right, that's improved only 4%, doubling every 18 years. The integer instructions per clock cycle, per core, is only improving at a rate of 7%, which means it doubles every 10 years at that rate. Number of cores doubles every 5 years. DRAM bandwidth every 7 years. Single precision floating point throughput. That one actually is matching the technology. But the problem is that no one does floating point on CPUs. They use GPUs. If you have a floating point intensive application, you're going to use a GPU for that. So even though Intel is doing very well with their floating point, they're still 10 times slower than a GPU, even at this rate. So why would anyone, it's kind of useless. In fact, Linus Torvalds has famously said that, he says this is a total waste, that there shouldn't be any floating point on CPUs at all. It's, that's wasted. There's better things to put on there with that space. And then the level 3 cache is improving at 12%. So basically what this is saying is that the actual CPU performance, as we've already seen, is not increasing with Moore's Law. And when I was a kid, I thought it was kind of an interesting anecdote. I'm not sure, some of you, I think most of you are younger than I am, but in the 90s, every computer actually had a turbo button on the top that when you turned it off, it would cripple the speed, because CPUs would get so much faster from generation to generation that you'd want to slow them down. So you'd turn the turbo, because some software just would break. In fact, if you look at my, when I did the video version of this course last fall, I showed a little, like, kind of a graphical example, like and I actually experienced this. I had Chuck Yeager's Advanced Flight Trainer, which is a flight simulator, and when I upgraded to the 286, it would run so fast that you couldn't fly the plane. It was unplayable. And so, but you'd notice that you never see these turbo buttons anymore. They got rid of them because just not needed anymore. You don't see that kind of advancement anymore. But you might have also noticed that recently, you always hear about, well, in general, in recent years, you hear about new capabilities all the time. You hear about, cars, the self-driving cars, and this is a little out of date too, but, I remember when 4K video came to phones in 2015, that was a big deal, because I was like, there's no way you're ever going to be able to record 4K on a phone, but that happened. And then Face ID, animojis, computational photography, all these things have, we're getting all these new capabilities. It's like, well, how are you getting all these new capabilities if CPUs aren't getting faster anymore? What's going on? Well, part of it obviously is advancements in the algorithms, but a lot of these algorithms are not necessarily new. And most of this is machine learning, and the concepts behind that have been around for a long time. What's changed is the performance. That these processors are becoming more performant. So it's like, well, but that doesn't make sense. How are they becoming more performant? Well, it turns out that the way this is happening is that it's through specialization. If you look at a die picture of a typical embedded processor, like the Apple processor, and this is, I've got pictures A5 to A10, obviously now they're at the A15 or whatever. But you notice that only a very small portion of the die, the actual chip, the real estate on the chip, is actually the CPU that runs the operating system. Most of the chip real estate is taken up by a collection of special purpose processors. And you might say, yeah, I know there's a GPU. No, there's more than just one GPU. There's usually like 8 to 10 different specialized processors that run in the various parts of this chip that are designed for specific tasks, meaning that the actual CPU in your phone does almost nothing but run iOS or Android. All of the heavy lifting when it comes to computational photography and augmented reality and animojis and all that stuff is all handled by specialized coprocessors that are designed specifically for that task, and the software runs for those on bare metal without an operating system or some very thin real-time operating system. Now you might say, well, what do those look like? Well, you never hear about them very much. They're coprocessors, and they're very highly secretive to the companies that design them. They're very proprietary. Now, they're still von Neumann processors in the sense that they fetch and execute instructions from a software stream, but they're very specialized. They have very specialized instructions, and they're generally programmed in assembly language or at a very low-level intrinsic-based abstraction. And so that's basically what's happening here. So what's my point? My point is that in order to deliver all these new capabilities you're seeing, what's really happening is that you've got teams within Apple and Samsung and these other companies, TI, they're spending a lot of time, in Tesla, they even have their own chip now specifically that they designed for their cars. They sit there and they design hardware, basically, is what's going on. So all of these new capabilities we're seeing are the result of hardware design, not software design. So, and this is the reason why, why we're teaching hardware design in this class. Now, obviously, to get a job where you're doing that, it's a very specialized, high-level job. But I mean, as a computer engineer, that probably should be one of your goals, one of your potential goals, career goals, is to have a job where you're doing this kind of design of specialized hardware to deliver these new, cool capabilities. Now, desktop processors, surprisingly, the same thing is happening. This is a die. Now, one of the things I like about Intel actually releases a die picture and they annotate it for you, right? Apple doesn't do that. These pictures, these annotations were done by this website called I forget the name, but there's a website that they go out and they try to figure out what's on the Apple chips based on the dye photograph, the micrograph, you know, microscope image of the chip. But Intel actually does it professionally, real nice for you, for whatever reason. They've always been very open about that. But if you go back to the Westmere chip that was released in 2010, you can see that the actual cores and the caches together are 72% of the die area. So this was 114 square millimeter die, and 82 square millimeters was the CPU and the cache. Then you go to the next processor architecture, the Ivy Bridge, and you can see that the actual CPUs are only 47% of the chip. And of course, you can see where this is going. You get to the Broadwell chip in 2015, and only 20% of the chip is CPU. Now, what's the rest of it? Well, basically what's happening is that Moore's law is keep going. You can fit all this stuff on these chips, but they're not using that real estate. They're not using those extra transistors for adding more cores or putting bigger CPUs or even bigger caches. They're using that for graphics, specialized processors. They're using it for co-processors. Now, what does that look like? What's the instruction set of that thing look like? You know, where's the documentation for that? Unclear. It's trade secret. You know, this stuff is nice and open, but this is all black box, right? Basically, right? And it's designed just to accelerate multimedia, machine learning, graphics, that kind, to make video games run better, basically.
Case in point, right? Try, you know, real-time decoding 4K video content on like an old, like 2008 era, like Xeon, and even though it might have like 16 cores. You can watch it sit there and tag all 16 cores at 100% doing video decoding because it doesn't have the coprocessors to operate on that video codec. Whereas right on a modern laptop, right, with an i7, 1187 or something, right, you can play that same video with almost no CPU utilization because there's an on-die decoder that handles that.
Yes, all the expensive computations are being relegated to specialized hardware. Yes?
So the previous slide, please.
Yes.
You have 4 cores in an Apple chip, no, Intel, it's quad core, 4
yes.
processors,
yes.
one chip.
Yes, yeah, this is one chip, and there's 4. So if you go back, you might notice that, wait a second, hold on, there were 6 cores on this chip, and there's 4 cores on that chip, and I tried to get pictures of. I try to make them as consistent as possible, but you'll also notice too that the die size has changed quite a bit too. So it's not comparing apples and apples, but there is a trend toward bigger graphics.
Parallel processing at the chip level.
Yes, yes.
Multi-threading is because of this.
Oh yeah, yeah. Having multiple cores is pretty standard now, but also it's also becoming standard to have not only processor graphics, a GPU on here, but also notice the system agent, display engine, and memory controller. They put big memory controllers on here to speed up memory access and I/O. Down here there's an eDRAM controller. I don't even know what the heck that is, but it's some kind of specialized logic specifically to speed up something other than the CPU.
Intel used to have a bus, 8085, 8086. Where is the bus here? The data bus, or I don't know what.
Oh, the bus is external. So this is just a picture of the die. So what they do is this die is bonded to a package, and then the package has pins that go down into the board, and the wires come off are soldered to the pins, and so that's not being shown here. In fact,
we cannot even access the port. There are no pins beneath the port, are there?
Yes, they are. They're not. I think there are. In this case, normally the pad frame is along the outer edge of the chip. But they might be using I don't know if they're doing flip chip bonding on these, or I'm not sure how they bond these to the package.
Do you have pins on all 4 sides or only opposite sides?
They used to be on, I don't think it's on the opposite because you need through.
Like the Motorola 6000, all opposite sides?
No, I think they're probably on, they probably what they did in this picture, my guess, I'm not sure. I never noticed that before, but I'm guessing they omitted the pad frame. So typically there's going to be pads, which are square landing spots for soldering wires, doing wire bonding I actually used to do that when I was in grad school. It's like a sewing machine. You know, it goes down and you stamp it on the chip, and then you stamp it on the package, and you go back and forth like this, and then of course you can automate it. But they're probably not showing the pad frame. Either that, or the pad frame is so small that it's not even visible in this picture, because I'm not sure how big their pads are. Yes?
I believe there should be some input-output, like memory controlling or some kind of outside output. And then when you have those transistors, they have aluminum wiring from that transistor, and then they can spread them to one side or spread them on the whole square side and then solder the pins.
Yeah, that's basically what I'm saying. Yeah,
And
you have to wire up the pad frame.
if you want to get access to the course, you do not necessarily should break the package and do whatever you want with the die. You can, they test their chips by sending special signals to the pins and reading the response from that.
Yeah, I used to do that too. I used to have little micro positioners, and we'd actually put a little probe down directly on a pad to test chips. Yeah. Okay. Okay, and here's just yet one more example, or actually I have two more examples. So this is the Qualcomm Snapdragon has a six specialized processors for DSP, audio, location services, display, camera, security. The Apple 11 Bionic has a 600 teraflop per second neural engine on it, which is pretty incredible. It's used for Face ID and the emojis and stuff. It has a GPU, and it has a motion coprocessor for the photography part of it. And then, of course, NVIDIA, they designed a chip called the Xavier that was designed for Tesla. And then Tesla decided that's not fast enough. We're designing our own in-house one. So they threw they threw that away, and they designed their own house processor called the NVIDIA or the Tesla drive. Yes?
What is the +3? Quad-core?
+3. That's the CPU +6 coprocessors. Yeah. Sorry, that's not very clear, but yeah, it's the CPU, meaning CPU that can run any software ever written, plus 6, coprocessors that are specific to a particular application. Yeah. Now, those coprocessors are specific, so sometimes they might be limited to 8 bits of precision. They're not general purpose, right? Only the CPU is general purpose. And then in the data center, that's happening. Of course, data centers and high-performance computers use GPUs, and Intel tried to have the Xeon Phi catch on, but it never did. It's mostly now they have these neural coprocessors and that kind of stuff. Okay, so you might ask, one question you might be thinking is, why is it that a specialized processor is so much faster than a CPU? Right? Why do we need all this specialized hardware? What is the advantage there? That's a good question. I wondered that when GPUs first came out. I was like, oh, GPUs are 10 times faster than a CPU. I was like, why? Well, there's two reasons. Basically, there's two things that limit a CPU's performance. There's the memory wall, which basically is it's when the memory bandwidth limits the performance of the chip. So basically, when you're spending most of your time waiting for data to come in from memory and not utilizing the on-chip resources of your CPU. That's called the memory wall, right? DSAs, or domain-specific architectures, these are the coprocessors I've been talking about. They're able to get around the memory wall by having large, specialized on-chip memory that are called scratch-pad memory, as opposed to just general-purpose caches that CPUs have. They get a lot of mileage out of that. And also, they have basically the software controls the scratch pad, so they can prefetch data while they process the previous batch of data. It's called double buffering. That's something that CPUs just can't do. Then there's the power wall, is another big one. So CPUs are fundamentally limited to dissipating 1 to 2 watts per square millimeter. You just can't go beyond that. If you go beyond that, it's too hot. You can't extract the heat. And so that creates this thing called the dark silicon problem, which says that even if you don't have the memory wall, even if you say, I can have all my cores and all my functional units working at 100% utilization, you still have to shut some down in order to limit the power consumption. And so so both of these problems essentially is limiting the utilization, how much of the chip you can actually utilize. And the other problem too is that because CPUs are general purpose, even without these, you can't utilize the whole thing, because if you've got, like, for example, floating point units on the CPU and you're running integer code, the floating point units are wasted. They're not used. They just sit there idle, right? Likewise, if you're doing floating point code, you've got spare integer units that aren't doing anything. So a domain-specific architecture, because it's designed for a specific application, you can boost the utilization of the hardware up, because you can only put in there what you actually need for the application. So if you're doing a neural processor for doing animojis, obviously you're not going to waste hardware with things that aren't required to run an animoji. So you get higher utilization and thus higher performance and higher power efficiency. So that's the reason, that's why these specialized processes are needed in order to be able to unlock these new applications. Okay, so let me switch gears here a minute. Let's see how much time I have. Good. So I alluded to this earlier. In this course, our objective, in a nutshell, is to build a RISC-V CPU from scratch using hardware description language, which is the way that all large-scale digital designs are made, and deploy it onto an FPGA, which is a field programmable gate array. It is a electronically reconfigurable chip in which you can essentially take a hardware design and you could make the FPGA behave as that hardware design without having to fabricate. Right? Now you might say, why don't we fabricate? Fabricating a chip takes a long time to get it fabricated, and it's not practical to do that within one semester. If we had a 2-semester sequence for that, we could do that. We could design it in the first semester, send it off to the fab in between semesters, and then get it back the second semester and test it. But there's a lot of overhead to that too, because you have to set up a testing framework, and it's tedious and it takes more time. FPGAs have the advantage of it's a faster turnaround. You can take your design, you can simulate it and validate it, and then you can essentially burn it onto the FPGA, although you're not burning it because it's only a temporary configuration. But you deploy your design on the FPGA, and the FPGA then behaves as though that's the hardware on that chip. Does that make sense? The downside of FPGAs is that the clock rate will be about 10 times slower than if you had fabricated your own chip. And also the number of gates that you can put on the FPGA is about 10 times less than logic gates, is about 10 times less than if you had fabricated. So essentially you're limited to about 200 megahertz clock rate, and this chip has about 115,000 gates on it. So an equivalent size ASIC would be 10 times as many gates and 10 times the clock rate. But the advantage is that you can turn around your design very fast. The other problem with ASICs is that, and you guys probably haven't heard this, but at companies that make ASICs being customized circuits that you actually fabricate chips, usually it takes more than one try before you get it right. They have silicon revs, they call them. They have Rev 1, Rev 2, Rev 3. So Intel might go out and fabricate one rev of their new processor, but then it comes back and there's problems and they got to go back and send it through again. So if we did this in a class, you'd only have the opportunity to do one revision, whereas with the FPGA you can do multiple revisions. You can test and deploy and test and deploy. And in fact, Intel even tests out some of their hardware on FPGAs. They do emulation with that. I had a student that actually worked there and did that. Yes?
The entire thing will be the chip we design.
Well, okay, so the FPGA, that's a good question. This is the FPGA here. It's the biggest chip on here. The reason we use this board, and you might say, well, what's all the other crap on there? Well, it's all peripherals that you can use to interface with the chip. So this board has switches and buttons and 7-segment LEDs, 7-segment LEDs, an LCD display. It has it has Ethernet and serial port and parallel port and GPIO and high-speed mezzanine connector and 3 USB ports and infrared port. It's got a bunch of stuff on it. So it gives you the ability, and it has 3 different memories, actually 4 different memories. It has DRAM, SRAM, soldered flash, and an SD card flash. And it's got SMA for high-speed clocking, and it's got what else? I guess that's about it. Oh, it has audio, has an audio chipset. It has a TV decoder chipset. So it has A to Ds, D to As, VGA out, which we probably won't get to. We used to have a project where we use the VGA, but mostly in this course we're going to be using the switches and the 7-segment displays and the buttons. But basically it gives you the ability to physically interface with your hardware. And that's what we want to do. Students in this class in the past have appreciated the fact, based on the feedback we get, that they can design hardware and they can physically interact with it through, physically throwing switches and hitting buttons. And so that's what these boards are great for. They're pretty expensive. You can get a cheaper version of this, but it doesn't have all of the components on it. So you can still, you can buy a smaller version if you wanted it and still put a design on there. It just doesn't have all the nice widgets on it that you can interact with, essentially. Yes?
Is there a prerequisite to take this course if you don't know Verilog or VHDL?
Yes, yeah, you're not required to know that. However, and that's a great segue, so it is critical that you understand assembly language. Because in this class, our objective is to design a processor that fetches and executes instructions. Now, so we have this, you guys hopefully, unless you're a grad student, hopefully you've taken 212, which is a prerequisite. Yeah. Half of the semester of 212 is supposed to be about assembly language programming, right? Now, the problem is that, yes, question?
Are we going to be working with MIPS?
Well, not quite. We've switched from MIPS to RISC-V. RISC-V is almost the same as MIPS, though. They changed just enough to not make it a copyright violation, essentially, right? So MIPS was owned by MIPS. And there's the guys, they wanted to make a free version of MIPS. So they made the minimal number of changes so they wouldn't get sued. That's basically what RISC-V is. So there's not much difference. They also made some changes in RISC that are actually nice from a design perspective, which I'll talk about as we go. But basically, they're very, very similar, right?
In fact, the tool we're using for it, RARS, is a fork of MARS that has been patched to support RISC-V. So if you use MARS in 212, it's the same thing. It just has an R instead of an M, and it does RISC-V.
And that's the only reason we didn't switch to RISC-V earlier, was because we didn't have a nice simulator like MARS. But once they came out with RARS, I was like, yeah, we're going to pull the trigger on this. But RISC is becoming, there are some that believe that RISC might replace ARM as the dominant instruction set architecture for phones and tablets and that kind of stuff. Now that might not happen because ARM is very aggressive in their marketing. But the advantage is that RISC is free, and so the licensing costs are a lot less. So if companies, like if Apple were to switch to RISC, they'd save a lot of money in having to pay MIPS, or having to pay ARM rather. And ARM, I think, was recently bought by NVIDIA. So I don't know if Apple wants to pay. If Apple doesn't feel comfortable with sending NVIDIA a bunch of cash, they might switch to RISC-V. So, but ARM is also very similar to these guys too. So anyway, you guys learned about MIPS. If you remember stuff from 212, then you'll be fine switching over to RISC. If, on the other hand, you had an instructor that didn't cover it very thoroughly, or if you just don't remember because it was 2 years ago, right, that you took 212, then you're going to have some problems in this course. So as a result, I am going to start out with an introduction, not an introduction, but a refresher. I'm gonna review everything that from 212 that you need to know for this course, which is essentially assembly language programming. Now you might say, wait a second, hold on. Who in their right mind would write code in assembly language when we have really great compilers, right? Yes?
I remember the pain.
Yeah, it is painful. It's painful for, yeah, and it's, even for me, I've been doing it for a long time, I still hate it. It's painful, right? And the answer to the question is no one. No one does write code in assembly language. If you need to access like an obscure abstraction that the compiler might not generate, then you can use an intrinsic, which means that you can access specific instructions from C. Use an intrinsic. So no one really writes code in assembly, but because we're designing a processor whose job it is to actually implement this assembly code, you obviously have to understand the assembly code to do the hardware design, right? So I'm not saying that you guys are going to be writing a lot of assembly code, but if you're designing a processor, you're going to have to design that processor to be the job of the processor is to run the assembly code, or the machine code, which is basically the binary representation of the assembly code. So obviously you have to be comfortable with assembly code and machine code in order to do the hardware design, right? So this is the reason why some 212 instructors say, what's the point in teaching assembly language? No one's ever going to use this stuff. Yeah, but unless you're designing the CPU, in which case you have to understand it. So that's why I'm going to cover this stuff. So hopefully you guys remember that there's really two important terms here. There's instruction set architecture, and then there's microarchitecture. They sound the same, but they're very different. Instruction set architecture, and sometimes that's just called architecture, is you could think of it as the native language of the hardware. It's the actual language that the CPU executes natively. From the hardware actually runs natively. Any other language you program a CPU in has to be translated to the assembly language. Now it's either done offline with a compiler or it's done online with an interpreter, which is what Python does. But either way, you have to convert, any high-level language has to be converted ultimately to the machine's native language before it can run. Now there has been some companies in the past that have tried to do hardware interpretation. There was a company called Transmeta back in 2000 that was founded by Linus Torvalds and Paul Allen, and they had this technology where they were actually going to translate a language inside the CPU, but it failed, so it never worked out. So unfortunately, all the CPUs nowadays, they can only essentially run their own assembly language, their own machine language.
I would point out, right, AMD 64 compatible CPUs are able to also run i386 instructions.
Right, yeah, well they microcode it.
One exception.
Well, that's a one-to-one mapping though. I'm talking about an actual, something more substantial than just translating one instruction to spitting out like a lookup table. Yeah, I mean technically Intel CPUs don't run Intel assembly. They actually translate into microcode, but it's a very straightforward, simple transformation. It's not like converting Python to assembly. It's not nearly at that level. But basically, that's the idea. So what is the assembly language? It's a repertoire of primitive operations. And when I say primitive, what I mean by that is the amount of workload that is performed by one instruction is very small. In fact, it's the smallest amount of workload that the CPU can execute. You could think of it as like an atomic bit of work that the CPU does. And so basically there's three main things that an instruction can do. Number crunching, compute, right? Like add, subtract, multiply, divide. Or load and store, which is to interact with the memory, the external memory. Or control instruction, meaning to branch or jump, like to jump somewhere else to implement a control construct like an if statement or a loop, right? Those are the three main. Now there's other instructions, there's interrupt handling, there's syscalls, and there's IO, but generally speaking, when you write assembly code, you're really just, each instruction is really just doing one of those three main things. You're either doing, compute, load, store, or branch, jump, control, right? And so as I mentioned, there's an assembly language. This is what you actually would type out. It's kind of a human readable text representation. And then there's a binary encoding of that where you can translate each one of those. You translate each one, there's an assembler that translates each one of those instructions to a binary representation that's actually run on the CPU. You guys have to understand both because you're going to be writing system Verilog that's going to be interpreting the binary representation of these instructions and then implementing them using data flow paths. Register transfer paths, right? So it's important that you understand not only the assembly language, but the machine language. Now we're going to have you write in the first lab a short assembly language program just to make sure that you're familiar with how RISC-V works. It's not intended to torture you. It's so you understand enough of it in order to be able to implement it in hardware. But also, we're going to take that same program. I mentioned the labs build on top of each other. That program we write in Lab 1 will be used as your test program for your CPU, or one of your test programs. So you'll be able to run it on your CPU. So just to give you a quick preview, the program will calculate the square root of an input number. And so when you have that program running on your CPU, you'll be able to enter the number through the switches. The CPU will calculate the square root through a combination of the assembly code you wrote and the hardware that it's running on, and then it will display the answer on these hex displays. So you'll be basically implementing a calculator, essentially, but from scratch and developing both the hardware and the software for it. So that's kind of the 10,000-foot view.
That's the first lab?
Yeah, that's the first lab. Well, the first lab is just the assembly code. We used to have you do both at the same time, but that was that's how we did it last fall, and I thought it would be better to split it up. Okay, so just to give you a little bit of background here, just so you guys you can see this in context. There's a lot of ISAs around. You might have heard of some of these. Of course, there's Intel is probably the most well known, possibly one of the oldest. Intel was notable that they were the first company to actually put a whole CPU on one chip. Because prior to that, like for example, the IBM mainframe and the VAXs, they had a CPU, but it was multiple chips, right? Intel said if we can bring all the logic required for a CPU on one chip, it'll be a lot cheaper to manufacture these things. And that was the innovation. And then they could sell an IBM PC for $1,000, whereas before that you had to buy a mainframe. It was like $1 million, right? So that's the idea. Now Intel has the thing that's a little confusing about ISAs is the naming. What happens is that you'll have an ISA and it evolves, it grows. Or sometimes it gets smaller because a company will say, hey, we're going to come out with like ARM, for instance, says, we're going to come out with a thumb instruction set, which is a variant of ARM that's designed for really low power CPUs. It's a 16-bit architecture, right? So sometimes the instruction sets grow, sometimes they make smaller, more compact, more efficient versions of them. So it's really hard to describe a whole ISA with one term now. Now they have optional modules, right? So for example, Intel, they call it the Intel x86, but it's actually comprised of two subtypes. There's the IA32, and then there's the x86-64, right? Two types, one's 32-bit, the other 64. They also have an IA64, but they abandoned it. They got rid of it. They killed it. That was the one that ran on the Itanium processors. Then you've got like Alpha and Spark or older ISAs, and then of course there's ARM. ARM has been coming out with a sequence of instruction sets. The old original Raspberry Pi ran version 6. Then then there was version 7. Then version 8 was when they introduced 64-bit, and now they're about to release version 9. And then within ARM, they have extensions like Neon, and the newest one is called SVE2, which are their vector extensions. And then, of course, you guys know MIPS, and then there's RISC-V, and even RISC-V is subdivided into multiple subsets, two of which we're going to target, which is called RV32I and RV32M, which is basically the 32-bit integer and multiply components of the RISC-V instruction set. I mentioned there's this other term called microarchitecture, so that's much different. Microarchitecture is what's under the hood. It's the underlying design that implements the ISA. If you asked Intel, like Intel is very forthcoming about their ISA because they want to give you their ISA so you can write code for it, right? You could develop code, you sell code. But they won't give you the microarchitecture because that is their trade secret. Like that's the underlying technology, the underlying design. So you'll never learn anything about the Intel microarchitecture. That's super, super, super secret. But yet, the ISA is something that they deliberately try to disseminate as much as they can. So the ISA and the microarchitecture are very different, right? You guys are going to be actually, I'm going to give you the ISA, which is RISC-V, someone already built it, and you're going to develop the microarchitecture for it. Okay, and obviously the ISA has to be consistent if you want to be able to run code, legacy code, right? So you have to be careful that your CPU adheres and checks out and it accurately can run the ISA, right? So ARM actually has a thing where if you design an ARM processor, you send it to them and they actually certify it whether it correctly implements the ARM ISA, because otherwise you could sell that and then people's code will break when run on your processor and then it makes ARM look bad, right? So, okay, anyway, so that's, I guess I'm out of time. So we'll see you guys on no lab this week. Don't come to lab this week. But next week, we'll have lecture on Monday, and we'll have our first labs, okay? And start looking for group partners, groups. Start forming your groups.
So how many are in your group?
2.